In this session, I would like to talk about disk and its various components and how we are going to store the data and what is the capacity of data you can store and how fast you can retrieve. Okay, everything. First of all, let us start with this picture. This is called a plate. Okay, so your disk can have multiple plates. This is one of the plate. So your plate is divided into like this. One is track. So we will be studying what is track, what is sector. So in a plate, you can see this kind of circles. Each circle is called a track. This is a track, okay, where you are going to store data. So in each track, we will be having some sectors, okay. That means track is divided into sectors. Finally, disk is nothing but set of plates. Each plate has set of tracks. Each track has set of sectors like this, okay, where in each sector we are going to store the data. In between the sectors, generally there will be a gap, that is called intersector gap. Similarly, in between the tracks, generally we will have some gap, okay, that is called intertrack gap. So these gaps are generally useful in aligning your input output, that read and write head tape properly, okay. So that details are not really required, so that unnecessarily dilutes our topic. So that's why we are not focusing on why that gaps are required, what is the width of the gap, everything. That details are not required, don't worry. Now apart from that, we will focus on so how much amount of data we are going to store and how we are going to store. So generally how we store the data is, so we select a track, and in this entire track, sorry, this is track, so we select a track, and in this track we will try to write data in sector 1, maybe after that sector 2, after that sector 3, after that sector 4. That is the way usually people write the data. Remember one thing, so how to write the data, where to write the data, and which addresses we have to use to store the data, that entire thing is decided by operating system. So that's why we don't bother about the details. But assume that, let's say, really we have to store in track number 1, then how we store the data we will see, okay. And what is the delays involved, that is what very important for us. One thing is, what is the capacity of the disk. Now I will tell you how to find out capacity of the disk, okay. If you want to know the capacity of the disk, first you should know number of surfaces. Sir, what is surface? Generally when you have a plate, that plate, this is called surface. So a plate can have, two surfaces, right, at most. You can use one surface or two surfaces to store the data, right. So that's why number of surfaces are important. Now example, let's say a disk has some 10 surfaces. This kind of details will be given in the exam. 10 surfaces, and each surface has how many tracks? Let's say 20 tracks, okay. Now each track has, let's say, 50 sectors, okay, and they will clearly give you the size of the sector. Example, let's say each sector can store, it depends on the machine characteristics, that's why that detail will be given. So the each sector size is, let's say, 512 kb, 512 kb. When these are all given, then the question is, what is the size of the disk? Very simple. First we will see the number of surfaces, 10, right. So first we calculate size of the sector. What is the size of the sector? 512 kb. If you have only one sector, then the size is 512 kb, but we have multiple sectors. How many? 50 sectors. That's why the size will be multiple of 50, right. 50 into 512 kb. That means I can say that in 50 sectors we can store 50 into 512 kb of data. But we know that 50 sectors, this 50 sectors per track, right, that is clearly mentioned. Similarly, so 10 surfaces per disk, we have 20 tracks per each surface, okay. Try to understand if that is the case, and each sector size is 512 kb. Now you see, since each track has 50 sectors, then I can say that this 50 into 512 kb is nothing but track size. But track size is not sufficient. If you want to know the disk size, we should know number of tracks. How many tracks we have? See, 20 tracks per surface. That's why I can say that the number of tracks per surface is 20. But that is not sufficient, because we have 10 surfaces. Each surface has this much space, then number of surfaces are 10, then how much space they will occupy? 10 into this much. That's why answer is 10 into 20 into 50 into 512 kb. Now we'll come from right to left, I mean from here to here. Okay, see, you have 10 surfaces, each surface has 20 tracks, then we have 200 tracks. So these 200 tracks will have, each track has 50 sectors, then 200 tracks will have 200 into 50 sectors. Now each sector has 512 kb, then these many sector will have this into 512 kb data, right? So this is the disk capacity. In that way, easily we can calculate disk capacity. Apart from that, we have to focus on the delays. Okay, so what is the delay here, how we are going to store the data, and how we are going to retrieve the data. If you understand, then you can understand the latency related to this disk. What is the latency? You know, the time required to take the data from the disk. So these here, generally there will be three important delays which should focus. One is seek latency, second one rotational latency, third one data transfer time. I will teach you one by one. Okay, so data transfer time. First of all, to understand all these delays and why these delays happens, you should understand how data is stored. Okay, let me show that. So generally what happens is, there will be read and write head. Okay, for each plate one read write head will be associated. Okay, so there will be an actuator. So this actuator will have various lot of heads. Okay, like this, read write heads. So each head is going to point to a particular plate. If you have 1, 2, 3, 4 heads, then you might have 4 plates in the disk. Understand? Now, what are we going to do is, so each read and write head is going to be moved slowly like this. Okay. Example, let's say you want to store in, say, this particular area. Then what we have to do is, initially there will be read write head corresponding to this plate that should be moved. For that, there will be a big component called disk controller. Okay, so disk controller will have electronics related to, or circuit related to this idea. Okay, one thing is what, now let us focus on only one read write head first, because we have only one plate, right? So that read write head will be like this. Now slowly that will be moved to a particular track. Once you place that read write head on particular track, then we have to go to the right place to write the data. Example, let's say you want to store data in a particular place. For that, we have to mention the address. Generally the disk addresses will have 3 components: plate number, okay, plate number, second one track number. I'm assuming that, let's say, each plate has only one surface. If you have multiple surfaces, you should mention the surface number also. I'm assuming only one surface for each plate. Then plate number, track number, then sector number. This will be a typical address of any sector. Okay. Once you mention plate number, track number, sector number, we will be storing the data. Example, let's say sector number. Sector sizes are typically 512 kb, you remember, sorry, 512 bytes. Okay, so this will be the typical size. Maybe it may vary, depends on the machine. So 512 bytes, otherwise 1024, 2048, in that way. So these are the typical sizes of any sector. Example, you want to store some data, whatever it is, in a plate number something 5, track number 7 and sector number 9. Then how we are going to do is the question. Okay, you have an address and you want to store the data. What happens is, this IO head, whatever we have, let me assume that this marker is IO head. Okay, initially it is placed here. Slowly it will be, I am assuming that this is what, this fifth, this is the right plate number 5, track number 7, sector number, let's say 20. So since in our problem we have only few sectors, right? Let's say take sector number 2. Assume that this is actually track number 7. Okay, this is, let's say, plate number 5, plate 5. So whenever this address comes, then your disk controller will work such a way that your IO head will be moved like this. What happens, I am telling. Okay, how it happens is a separate story, that is not really required for us, but what happens is important. So your IO head or read write head will be slowly moved to appropriate, because already we are at right plate, right? That means the right head, because there are multiple heads, right? The right head will be enabled first. Then now we have a right head that has to go to 7th track. Slowly it will be moved like this, and slowly it will come here. Once it comes, that the read write head may not be pointing to the desired address. What is our address? I want sector number 2. Then we have to move this IO head like this, or read write head like this. But generally that is difficult. So your design, your architecture will be designed such a way that, otherwise your disk is designed such a way that, so plates generally will be rotated. So that's why when your IO head comes here, that means your read write head comes like this, then your plate will be rotated so that the right sector will come under this read write head. So example, let's say you are at sector number 1, right? Then your disk controller will know how to move your plate such a way that S2 comes under read write head. So once it comes, that means plate will be rotated. So finally, end of the day, what happens is the right sector, this is, let's say, right sector S2, then this will be the final picture. In that way, your read write head will come under the right sector, such a way plate will be rotated. After that, now you are able to store the data. Usually we store the data in sectors. That means a huge amount of data we store at a time. Usually we store data in blocks or sectors. That means example, sector size 512 bytes. Generally what happens is, it would be good to store 512 bytes of data, otherwise 1024 bytes. We never store 1 byte of data in disk. Okay, generally we write huge amounts of data. Okay, so example, let's say I have some data to write in this second sector, right? Then now you are already, your header is, or head is pointing at right place. Then you want to write the data in this sector. Then again sector will be rotated. That means this plate will be rotated like this. When plate is rotated, then slowly you will be writing the data like this, 0 1 0 1, in that way. So that is what happens. Finally, what you have realized is, writing into the disk is nothing but first adjusting your read write head at right place. That means we have to identify the right track. To identify the right track, we have to move read write head, right? So read write head movement is required. That delay is called seek latency. The time taken for your read write head to go to the right track is seek latency. Then after that, what we did, once you go to the right track, then we have rotated the plate such a way that the right sector comes under read write head. So that is called rotational latency. So that takes a lot of time, like seek latency. See, why we are discussing all these details? Because these latencies are going to decide our future. That means if these delays are very high, then we will be taking a lot of time to access the data from disk, because most of the times we will be accessing data from disk, because that is a permanent storage we have, right? Whenever you switch on your computer, then data starts moving from secondary disk to primary memory or main memory, correct? At that time, if it takes lot of time, then you get lot of delay, you see lot of delay. We have to avoid it. That's why we have to understand what are the delays we have while taking the data, right? So that's why one delay we should somehow reduce is seek latency. Okay, now second one, rotational latency, because we have to rotate this plate. Once you rotate the plate, and once your read write head comes to the right point, example, let's say this is sector number 2, then we have to write the data like this, correct? So this read write head will have a capacity to write zeros and ones while you are rotating the plate. Okay, so again you have to rotate the plate, because example, let's say you are not rotating the plate after that, then always this read write head will be writing 0, then 1 0 1 on same place, correct? That's why, so this plate has to be rotated, so that when it is getting rotated, first we write 0, then when you rotate, then we can write 1 here, then here 0, here 1, in that way. So in the different places we can write the data, right? That is called data transfer time. So the major parameter in data transfer time is rotational latency, the rotational delay, because if this plate is slowly moving, then though your read write head is very fast to write the data, he has the capability to write data very fastly like this, 0 1 0 1 0 1, but plate is slowly rotating, then you can't do that, correct? That's why what people realized is, the data transfer time majorly depends on the plate rotation or disk rotation. Okay, so this is about all the delays. So now finally what I want to say is, it's always good to reduce the seek time. You tell me, one easy thing, otherwise one optimization, so that seek time will be reduced. To reduce the seek time, always try to write data continuously, right? So that's why. So don't write the data byte wise like this. So one byte today, then again another byte. Then what happens, you see, for every byte, if you starts from the scratch, then we have to have a seek latency. That means we have to adjust to your IO read write head. After that we have to write the data. Then we have to rotate the plate, everything, right? The best thing is, that's why we write bulk amount of data at a time. That is one thing. Second thing, we write data continuously, right? We don't write data randomly. So one optimization what we can do, completely all your continuous data should be stored in one sector. If that sector is full, sir, then go to the second sector in the same track. Sir, no sir, I fill first sector number 4. Once I fill the sector number 4, I don't fill sector number 3. I will go to another track. What happens? Then unnecessarily we have to move your read write head to the another sector, right? Sorry, another track, right? It takes some more time, right? There is a seek latency. To avoid the seek latency, then we have to completely fill the track. Then only go to the another track, so that we can reduce the seek latency. That is one thing you should understand. Second thing, sir, my track is completely done. I have filled all the track. There is no space. Then where to go? Once you fill this total track, probably at that time, maybe you can go to the immediate next track, rather than, so writing the data here, one sector. That means, track number 1. First completing track number 1, then track number 0, then track number 100, in that way. If you randomly move to tracks unnecessarily, you are wasting the time. That's common sense, right? So that's why the always good design. Example, you have huge amount of data. First of all, write in a particular track, then go to the next track, then next track, so that your IO heads or read write heads movement will be very less. Don't do randomly. That means, what is a bad design is writing data in random tracks like this, T1, then T100, then track number 20, then track number 75. Then unnecessarily your IO head, that means read write head, will be moved, rigorously, and that takes lot of time. We will see one numerical example that shows the differences between storing the data randomly and storing the data continuously. Okay, and you will realize definitely that storing the data continuously will have impact on performance. Okay, so this is all about basic details about your disk. Now we'll see one more parameter, that is density. So what is density? I will tell you. Density is nothing but the amount of data which you are going to store per a particular centimeter. Example, let's say you have this kind of track. In this track, maybe this is, let's say, 1 centimeter. So in this centimeter space, how many bits you can store? What is your capability? So that is nothing but density. Example, let's say you are storing let's say 30 bits per centimeter. Then we say that the density with which you are storing the data is 30 bits. 30, okay, 30 bits per centimeter. Similarly, we can use inches also. Sometimes we can measure it with like this, 50 bits per an inch, in that way, anything. So finally, it is nothing but number of bits per a particular area, otherwise particular length. Understand? Now what I want to say is, if you follow fixed density mechanism, that means if you maintain a fixed density, that means everywhere you will be fixing the number of bits which you are storing per a particular length. Then what is going to happen is, this is, let's say, innermost track, this is outer track. Then one observation is, innermost track will have less number of bits than outer track, right? Because outermost track has much space, like the length is more, right? So that is a problem. What is the problem, sir? Why don't you maintain this kind of variation, like in innermost track, let's say I am storing 1 KB, because the length of the outermost track is much higher than this inner one, then maybe I am storing 10 KB. So what's the problem with this one? So then calculations will be difficult. That means implementing will be difficult generally. So what happens? What is the what I want to say is, if you store equal amount of data per a particular track, then retrieval and such calculations will be easy. Example, let me fix it first. What I am doing is, rather than storing 1 KB here 10 KB generally, so one method people follow is storing fixed amount of data. Okay, fixed amount per a particular track, fixed amount per a track. If I do that, then what is going to happen, we will see. So probably here you will be storing 1 KB. Here also I will be storing only 1 KB. So finally the amount of data which I am going to store in a particular track depends on inner track, because inner track will have lesser capacity, right? That's why if it can only store 1 KB per a particular track, then I can't force this track to get 10 KB, right? Because that may not be possible. That's why what I do is I will store only 1 KB in the outer track, right? Now what is going to happen, you see. Example, when you have this kind of thing, then probably let's say you have head like this, read write head. When you have read write head at particular track, then if I rotate this complete plate, how much data you can get? 1 KB. That means it is easy for me to say that to get the data 1 KB we have to rotate the plate completely. Sir, I want only half of the 1 KB, 512 bytes. Then what to do? Rotate this plate only half period of time, correct? In that way, getting the data, that means getting 1 byte of data, 2 bytes of data, let's say if you want 10 bytes of data, everything is easy here. So same thing I can do here also. If you really want to have 1 KB, then simply adjust your read write head on a particular track and simply make a full rotation. If you do full rotation here, what is going to happen? We are going to get 1 KB of data. Similarly, what if I have my read write head in outermost track? Then if I rotate this plate, same thing will happen, because here also you stored only 1 KB of data. That means what? So here design will be simple. That means if I rotate it for some fixed amount of time, like whatever, like example 1 minute or 2 minutes. So how much time, whatever may be the amount of time, if you rotate the plate, you are going to get the same amount of data from inner track and outer track from any track, right? That is the advantage of fixed amount model. Understand? But there is another method called zone bit recording. So zone bit recording. In zone bit recording, what are we going to do is, for particular zone, the amount of data which we are going to store per a track is fixed. But when we go to outer zones, let's say this is inner zone, this is outer zone. When we are moving outside, then the number of bits which we are going to store per a track will be increased. In that way, I can say that in, let's say this is zone 1, this is zone 2. In zone 1, if we store 10 KB per a track, then in zone 2, for every track we will be storing 20 KB. In zone number 3, maybe you are storing 30 KB. In that way, variable amount of I can say variable amount of data we will be storing. But it is difficult. Already I told you the design, the previous design was simple, but here the design will be complex, because retrieving the data. Example, when you are in outer track, how much amount of time plate should be rotated so that you get the right amount of data, everything will be difficult. Further complex circuit is required, because when your tape head is here, then half rotation gives 5 KB. When your tape head is here, then half rotation won't give you 5 KB, it gives you 10 KB of data, right? Because we have 20 KB amount of data in particular track. So appropriate circuit should be designed so that the right amount of data, whatever we are asking, should be given. Okay, that will be complex, but that's enough. Like finally there are two models. Okay, so first one is second one is especially called zone bit recording. First one is called constant angular velocity recording. So where we will be fixing this angular velocity, that means our velocity was fixed in the previous one. Okay, so that's why the name is constant angular velocity recording. So names are not so important, that's why I don't want to focus on that, but try to understand the two models. But in the GATE exam, if they don't mention anything, then you follow first method, where in every track, simple, every track same amount of data, that's it. Okay, now what we do is we try to understand the remaining things, like so with this concept, whatever I taught you, right? With this concept you can answer any GATE question, but you need some experience, like there will be to answer the questions correctly. So you should understand some problems, example problems. While explaining example problems also, if I have not covered anything, I will cover it, understand, in that way. So what you do is just understand some 5 to 10 examples related to disk problems so that you can answer any gate question in the next year. Okay, we will see that.